Let's say I give you a system like this. This is a fixed wall. There's two strings attached like this, by which rigid body is hanging. The rigid body has a mass m. And I give you another system. This time a system of rigid bodies in this particular configuration within a container, each having mass m. Let's say I give you another one. This time a frictionless wedge, the mass m. Since this wedge is frictionless, the body will slide down on its own. To counter that, we are giving it an input force P that is keeping it in position. Okay? Or let's say I give you another system where this is a wall and one rod is inclined at this particular configuration, and there is friction here and friction here. Okay, so if I tell you, hey, find the equilibrium of these positions, equilibrium position of these positions, you know that there is one fixed equilibrium position for this kind of bodies. This one is a single rigid body, or SRB. This one is again an SRB, and this one is SRB2, while this one is a system of rigid bodies. Correct? And what's common is there is a proper equilibrium position for all these bodies. Now, what if I give you a system like this? Let's say there is a pin joint and there is a link which is again pin jointed, and there is another link like this with a roller at its end. And let's say there is a force P being applied here. If I give an angle theta here, can you define the theta that guarantees equilibrium for this system? It's difficult to say because the link will try to move like this, right? Under the application of a force, this might be another equilibrium position. You don't know. You just simply don't know. So this kind of system are called interconnected system of rigid bodies, where this one is a rigid body and this one is a rigid body, and they are interconnected here. Let me give you another example. You know IC engine, right? Internal combustion engine. Let's say you have an IC engine that is driving a crank. This is the crank that rotates, and this is the connecting rod that is linked with a piston within a cylinder. And due to combustion, it experiences a force here, and this goes to and fro. Because of this to and fro motion, this crankshaft rotates like this, and that is the basis of all automobiles that is running in the road, right? So this one too is a system of interconnected system of rigid bodies. And can you define equilibrium for this system? It's a little difficult. We don't know yet. So usually what do we do when we face systems like this? When we face systems like this or this or this or this, what do we do? What we usually do is net force in the x direction is 0, net force in the y direction is 0. We write equations. If that is not enough, we write net moment is equal to 0. These are called equilibrium equations. And these equations work perfectly for systems like this, they work perfectly. We know till now. But can we use these equilibrium equations for systems like this or like this? The answer is yes, but the solution becomes extremely cumbersome. or it becomes very difficult to solve. What you have to do is you have to isolate each of these links, then draw free body diagram, then all the forces that is acting, and then try to write all the equations, and that makes it very difficult. A better way to solve these kind of problems, interconnected system of rigid body problems, they can be solved by knowing the principle of virtual work, which I will cover in this module, in this lecture. So let me repeat. When you have a single rigid body system or a system of rigid body systems, like the first 4 diagrams, you can use these equilibrium equations because their equilibrium positions are well known. But on systems like this and systems like this, where the equilibrium position is a little hazy, we use the principle of virtual work. And these second kind of systems are called interconnected system of rigid bodies. Okay. Now, to understand principle of virtual work, we have to understand first what work means, work done by a force means. So let's start. So work done by a force, and that is defined by this notation U, is the dot product of applied force and the displacement. Now you will say, sir, that looks very similar to moment. Okay, so let me write down moment. Moment M is the cross product of force and displacement. So I hope until now you know the difference between a dot product and a cross product. So what happens is both the units are Newton meters, but we reserve Newton meter for only moments, and we use the unit joule for work done. And also you will realize that work done is a scalar quantity, which means we are only worried about magnitude and do not worry about direction, while moment is a vector quantity and we worry about both magnitude and direction of the final moment. Okay, so if you remember moment, you might remember we were very much worried about finding the perpendicular distance, right? But in work, we will try to make the displacement parallel to the force or the force parallel to the displacement. Let me show you an example to make it clear. Let's say there is a body and this is a solid ground and there is a force acting like this on this body, say F, and that force is acting at an angle of theta with the horizontal. And due to this force, the body has a displacement, which is this displacement. Let's name it del S. The body is now in this particular position. So what is the work done by this force F? That is equal to U F cos theta into del S. So where does this cos theta come from? Basically what we did is force is in this direction, we resolved it in this direction, parallel to the displacement. If you notice this equation, we can also write this equation as this, F into del S cos theta, which means we can resolve this displacement that is earlier in this direction parallel to the direction of the force in this direction. Both are possible. So that means the final work done does not care whether the work is going this way or the work is going this way. It does not care. And that's why this work is a scalar quantity. It does not matter. Okay. So this is what work done means, and the unit is joule. Okay. Now, what is virtual work? As the name suggests, virtual means something that is not actual. The work is not being actually done, but it is being done virtually, and the notation being used is du, and we will use the same formula, f del s cos theta. Okay, that is the notation for virtual work. Basically, the idea is for interconnected system of rigid bodies, since the equilibrium is not exactly clear, we make a virtual displacement, this, and we figure out the most correct equilibrium. And the principle of virtual work states that to find the equilibrium of a system of interconnected rigid bodies, this has to be 0. Basically, to find the equilibrium, this is a necessary and sufficient condition. Necessary and sufficient condition to find equilibrium of an interconnected system of rigid bodies, or basically this means f del s cos theta is equal to 0. So by applying this condition for an for an interconnected system of rigid bodies, you can find the equilibrium. So now, sir, can the principle of virtual work be applied in these kind of systems? Can they be applied for this? Can they be applied for this? The answer is a resounding yes. They can, but equilibrium equation does a far better job in solving the first 4 kind of problems. You do not need to use virtual work for solving those first 4 kind of problems. Virtual work does not offer any particular advantage for those kind of problems. Where virtual work is particularly applicable is this kind of problems, where there is interconnected system of rigid bodies, this kind of problems. Virtual work wonders, and this equilibrium equation, they make it extremely cumbersome. You will get the same answer, but you will have difficulty solving, or it becomes very hard. So that is the primary value of principle of virtual work. It works best for interconnected system of rigid bodies. So in the next numerical, I will show how principle of virtual work doesn't hold much advantage for the first 4 kind of numerical systems that we showed. And then in the second numerical, I will show the real power of virtual work. Okay, till then, have a good day.